Okay, so hello people. Today is July 28th, Thursday. We're going to go on with chapter 5. This is just a review of some statistics. Then we're going to introduce the concept of spectral density, okay, because we need that in order to describe the irregular wave situation that are coming into the ship. And eventually, not today, but hopefully in the next session, we will deduce an expression in order to calculate the spectral density of the response of the ship, okay? And for that, we need to describe the spectral density of the incoming waves. So that's more or less the material for this afternoon. In the second part of the class, okay, I would like to see if there is any problem with the analysis of the results of the experimental part that we developed last week. Okay, so everybody will be should be able to start right away because there's not plenty of time. Okay, and hopefully by the end of the session, you and I, we will agree on the itinerary for next week. Remember, next week we have an in-person activities. Okay, so everybody should be aware of that, and everybody should have a clear idea of the itinerary. Okay, dates and times for that. Okay, so let's start. I'm going to. Oh, Jesus, no, that's not what I wanted to. Oh, this is what I want. Okay. Can you see my full screen? People, can you see my full screen? No?
Yes, doctor. Okay.
Full screen?
No, not full screen.
Not full screen? Okay. How about now? Full screen?
Yes.
Okay, this is, okay, thank you. So this is what we reviewed last session, okay? This is the result of doing a Fourier transform analysis, okay? So basically what we do is we go from okay? And the result of the Fourier transform on a function f of t, okay? The result of that is another function, but in this case, it's a complex function, okay? And that function depends only on the frequency of omega, right? So on the right-hand side, we have some examples, okay? In this case, we have this function. It's a combination of these three harmonics. I did this in Excel, right? And then I imported from EasyPlot. And then in EasyPlot, we have the fast Fourier transform function. It's an application available in the EasyPlot. And on the lower right-hand side figure here, you have the result of the Fourier transform, okay? And there are a couple of things that we should be aware of, okay? First, this is 0. So on the right-hand side, you see that we obtain the same that on the left-hand side. That means that it's something that we comment last session, that if f of t is a real function, then the Fourier transform is going to produce a symmetric result. So this on the right-hand side is equal to the left-hand side. And we're going to take advantage of that in a simplification, specifically when we talk about spectral density, okay? And another thing is that here we have this, and that. These are three harmonics. And when you apply the Fourier transform, since you multiply this by ei omega t, okay, when you have omega of the same frequency of this or that, the result is going to produce an increment and a spike. And that's what we see here, Okay, that's something that we employed when we apply this fast Fourier transform in mechanical vibrations, right? To identify the harmonic component in a signal. And that's what you're seeing here, right? This is 1, okay? This is radians per second, right? If you divide by 2 pi, so it's about 1.15 or something like that, 0.15. And that's what you see here. See, this is 0.5, this is 0.25. So this is about 0.15 or something like that. So you have a large value. That's because proportional to this amplitude of 1. And then for 2.5 and 4, we have these 2 spikes. And you see that basically this is about half of that. And these 2 are very close between them. And that's proportional to this amplitude, 0.5. Okay, so that's a result of this, of the Fourier transform. So that's, I'm highlighting the characteristics of this operation, okay? This table is just to show you, okay, typical results of applying the Fourier transform or some common functions, right? For example, if you have the Fourier transform of the Dirac delta function, the result is 1. Now, here, I should obtain 1 divided by 2 pi. And why is not a 2 pi here? Well, the difference is that this table is usually, there are 2 versions of this Fourier transform. One is the Fourier transform that we as engineers work, right? And the other one is the one that is employed by mathematicians, okay? We prefer to work with the frequency in cycles per second. Physically makes more sense. Mathematicians, they prefer to work in radians per second. And the difference between these two is this 2 pi factor that it appears in our deduction, right? So don't worry, we are not going to, I'm not going to ask you to do these operations, but in general, it's a good idea that you have or remember, because probably you saw some of this in your math courses, right? Then we summarize these characteristics. This is something that we should have in mind. In general, okay, when you talk about frequency domain and time domain, basically you immediately start thinking that you are using the Fourier transform. Okay, so the Fourier transform takes you from the time domain, okay, a function which it depends on the time, and have as a return something, a function which it's in the frequency domain, right? It's a function which depends only on the frequency, on omega, right? And theoretically, you could go back, okay, but the problem is that usually when we obtain a Fourier transform, usually we tend to take the amplitude, okay? So it's like we lost some information, okay? Basically, we neglect or discard the phase shift, okay? If we had these 2 parts, amplitude and phase shift, we should go back from the frequency domain into the time domain, okay? Integrable functions. Does anybody remember what an integral function is? Anybody remembers this? Anybody? Or should I call somebody? Should I call somebody to help me, to remind me about this? What is an integrable function? Anybody?
A function that is continuous in the domain.
No, not only that, but remember that when we work with a Fourier transform, we integrate from minus infinity to plus infinity. Okay, so that means that immediately the result is going to be infinity, because remember that integration is the area below the function, right? So when we say integrable functions, that means that it's a function that when you increase the time, these functions tend to 0, right? So if you integrate up to infinity, basically the last part of the integral does not contribute much, and that will produce something which it's it's not infinity. Okay, so in our case, basically what we do is we take a finite integrate interval of time and assume that after that the function value is 0. Okay, otherwise we will, every time we integrate from minus infinity to plus infinity, we will get infinity, and that's something that we cannot handle easily. Okay, that's the interpretation of integrable functions. Okay, and this is one of the most useful characteristic, right? It allows us to identify harmonic content. Okay, and that's something that we did in the mechanical vibrations course. We took a function, remember the oscillation of a 2 degree of freedom system, and with that, after applying the Fourier transform, we were able to identify the content, the frequency content of in that signal. And the frequency content was a combination of the two natural frequencies of the system. So this is the most useful application of this Fourier transform. Okay, so basically that's the most common way we can apply it. Okay. As we know, the result is a complex function, right? But usually when we take a complex number, usually we tend to get the amplitude, okay? And we basically forget about the phase shift. So we basically discard some information, right? So in some cases, what we do is we can get the amplitude, and then if we want to go back to the time domain, what we do is we generate a phase shift, right, in a random way, right? So in this way, it's a practical way to go back to the time domain of the function, okay? But in general, that's what we tend to do. We get a complex function, immediately we take the amplitude and we discard the phase shift, but we lose information in this way. And finally, if f of t is real, and that's our case, right? In that case, the amplitude of the Fourier transform is symmetric. And that's something that I showed you a few minutes ago with this example that I prepared with the combination of 3 harmonics, right? So those are the characteristics of this Fourier transform. Then we did some review of this, some statistics. So this is just a review. What is a random process? Well, there are 2 things here, okay? One of the things is that it doesn't matter how you start. The end result is going to be different, okay? And that's why when we do experiments, we have to repeat, because we have to check that what we obtain is close to a probable value. It's a little bit different, but these results are close to one probable value, probable result. So what we need to do every time we do experiment is to repeat it in order to check that we indeed tend to this likely probable result. Okay, so that's something that we need to do every time, because in general, when we do experiments, there is no way we can avoid the randomness of some parameters that we have to include in the physics of this problem. Okay. Okay, and then we recall what the very first steps of producing this probability density function. Okay, we take an ensemble, which is a group of time registers, right? It's like this one. In this case, I'm showing 3, but there are in this group we have many of these. And then for a certain value of time, okay, we get the result from each one of these signals. Okay, like this one here, this, and that. And what we do is we split in the ordinates scale. We break this into intervals. And for each one of these intervals, we identify the median value, and we call it the class of each interval. It's like the name of each interval. Okay, in this case, this delta zeta denotes the size of each one of these intervals. Okay, so in this case, we see that this signal, one of these, it's in here in this interval, which is this class. And what we do is from each one of these time register, we identify in which one of these intervals is each one of these measurements. Okay, and from there we prepare a frequency histogram. Okay, in this example, I'm showing 20 intervals. Okay, for each one of these intervals, we have this class. This is like the mean value, okay, in each one of these intervals. It's basically the name of each interval. Then here, I have the number of times that we have one of these results in each one of these intervals. So we have a total of 7,201 time registers. This is a very large number of registers, right? And we need to do something in order to avoid having to do such a large number of measurements. It's a lot, okay? And after that, we ask ourselves, okay, let's suppose that I choose one of these intervals. And what's the probability that I take any of these values and it's in this specific interval? And this is the way we express that. That's a probability, please. This is large P, that this value is in this interval. And it's by common sense makes that we can express that as the ratio between this number from this ensemble divided by the total number of time register that we have in this ensemble. Okay. Now, the problem with this is, as we said, is that this depends on this size. So what we do is we define a new parameter, which could be seen as independent of the delta zeta, and that's what we call the probability density function, right? It is what we see here, the little p. Okay, so please let's avoid problems with or confusions. Probability is large P, probability density is little p. Okay, so if we take this delta zeta and put it on the left-hand side, and then in that case, the little p, it's independent of the size of delta zeta, right? So it is what we have here. And immediately, people, please, this is very important, is that the probability, large P, has no units. Probability density has units of 1 over the units of the variable that we are talking about. Okay, so be careful with that. This is engineering. So every time I ask you to do some calculations, we need you to specify the units of the result. Okay, in this case, we can take a limit. That means that we can talk about a very large number of registers. And of course, we can take delta zeta to be very small, right? So if we remember, the area under this curve is the integral, right? So if we plot this parameter, the area will be multiplication of this times this delta. So this will give you the probability. So if we plot this probability function, the area under that curve will give us the probability. So when we take this delta zeta very small, that means that n has to be very large, we can produce a continuous curve, right? And this area under this curve, as we have seen before, is the probability that you are in this interval from A until B, okay? And what people have done is to do for a certain variable, they can do many of these observations and then try to set up or do a regression, okay, on these values and produce a certain function. And what we can say or assume is that we can assume that this phenomena follows a certain rule. And of course, you recall that the most common is the normal distribution. Now, in the last slide, we saw that we need a very large number of measurements. But the problem is that we have limitations to do that. So what we're going to do is do two assumptions: that this random process is stationary. That means that we obtain the same result no matter for what time we take the information, okay? That means that we can take, for example, the values of these results at a certain time ti, and then we take the same information for another time, and in the results, the histogram is going to be the same. That means that the process is stationary, okay? Usually, when we do these calculations for the response of the shifting waves, irregular waves, we assume that the process is stationary. Okay, so we're going to say something like, okay, we're going to assume that the ship is navigating, for example, in sea state 4. That means that the distribution, statistical distribution of the waves do not change as long as we are in this sea state. And usually you can take, we can make this assumption for a certain period of time, okay? It's very difficult that you can assume that you have the same sea state for, say, a couple of days. I mean, you can easily imagine that after the usual time that we can consider to have a stationary process is 3 hours. It's very difficult that you can assume that the process is stationary after 3 hours. Okay, but in general, that's something that we're going to assume. And the other, which is extremely, extremely useful, is that the process is ergodic. That means that instead of doing this histogram with an ensemble, we can integrate in time with a single time register, right? So instead of having one observation from each one of these time register, we integrate in time with a single time register, and the result is going to be the same. So of course, we do a single time register for a long period of time, and that's enough. We don't need to make n, very large n number of time registers. So that's extremely useful. Okay, in this case, I complete the assumption or this example, and in the blue, so that's the histogram and the probability density function. And then what I did, I draw a distribution, assuming that the wave, in this case, it was the wave height or the surface elevation of the seas. It follows a normal distribution, right? So in this case, sigma squared is the variance, mu is the mean value. In this case, the square root of that is standard deviation, right? So in this case, with these two values, mu and sigma, you are able to develop this this curve, the red one, right? And we see that it's adequate, right? It's very close, right? So if we assume that the red and the blue are close, okay, and we know that the normal distribution of the red, and this is this function that I'm showing here, you can go on and calculate the probability, right? For example, what's the probability that you are in a certain rest, for example, between 0 and 2? In that case, what you have to do is you calculate the area, okay? In this case, I took this signal, right, that you see here, and I integrated in time and calculated the mean and the standard deviation. And I employed that in here in order to develop this red curve. And these are the values that I employed. And you see that the mean value is very small, very, very small. That's typical of the wave elevation, okay? You can expect that you go up positive values with the same probability that you go down negative values, right? That's what you expect the mean value to be very small. And this is standard deviation. So you calculate sigma squared, and then you take the square root of that. So that's a measure of the how distant you are from the mean value. Okay, in this case, this value it's a good one, right? That means that you had a lot of spread. Okay, you see that you have a lot of variation from the mean value. Okay, what else? We start reviewing some statistics concepts. So here I have the mean value. Okay, so if you have this function zeta of time, okay, of course you can imagine that it's difficult to have this function of a random variable, right? What we have usually is just values of this zeta. We don't have the function itself. But let's suppose you have the function. In that case, what you can do is you integrate for a long time. This big T is a long period of time, and divide it by the length of the period. And the result is going to be the average, right? Now, usually we do not have this zeta as function of time function, right? So what we could have is the probability density function. So if we know this, we can apply this formula to calculate the mean value. So this mean expected value is a good measure of this. Now, if instead of having the probability density, little p, we have an histogram, you can apply this formulation, right? And you can recognize that the product of this z times little p, that's a probability, which is equal to mi divided by n. So basically, this is it's a summation which approximates this integral. Remember that the integral is the summation to infinity. Okay. We also recall the definition of mean squared. Okay. So again, if you know this function, right? For example, in this case, you have this wave elevation, right? Surface elevation. The mean value would be very small, basically 0. But we know that you go up and down. So what we can do calculate is another function, another parameter. In this case, what we do is we square the function. So contribution from the positive or negative side will contribute to the summation. And then we divide it by the time length. And the result is something we call the mean square. Okay, that's this thing here. Again, it's not very common. I don't know if you have any random variable, and you know the exact function zeta of time. So what we usually do is we have a time histogram, and in that case, okay, we could apply this formulation in order to approximate this function that could be applied in order to approximate this. But in this case, you know or assume the probability density function. So again, this z times little p is the probability square. So this is a summation which approximates this integral. We have another statistics concepts, the variance. Okay, so it's the expected value between the value of the variable with respect to the expected value. So it's like how far away is this zeta from the mean value. Okay, that's the interpretation. By definition, that's the way you calculate it. Okay, and this, remember that this is a very common exercise when you do the statistics class, right? You expand this square and do some integration, and the result is this. Okay, so this is the mean square minus the mean raised to the second power. So please be careful with the words. This is the mean square, and the other term is the mean raised to the second power. Okay? So this is a very common statistics exercise, right? I'm sure you recall that. This is the definition of another very useful function in this area. Is what we call the autocorrelation. Okay, so it's auto. That means that with the same function, how it is correlated to itself, right? So what we do is we multiply the function by the same function, but shifted with a certain time interval. And this is what I'm saying here. So you multiply this point in red with this point here at a different time interval, and you keep summing this product, right? So you can imagine, for example, if you had this point here related to this point here, right? So if tau is close to the distance between this and these crests, the result is going to be a very large value. That means that the autocorrelation for a value of tau of this space between this and these crests is going to produce a large value. So it's in some sense it's similar characteristic as the Fourier transform, right? But in this case, you are working in the time domain. Okay, so if you have a function in the time domain and you calculate the autocorrelation, and you have a very large value, that means that for that value of tau, you have probably a function, a harmonic function with the same period, right? That's the result of that is a large peak in the autocorrelation function. And of course, if tau is 0, if this is 0, that means that you're multiplying this by itself. That's what we have here. And we know that this is a mean square, okay? So usually that's something that we said here last session is that the RMS, that's what we call the root mean square, okay, is the square root of the mean square. So if you take RMS square raised to the second power, that will give you the mean square. So it's you have to be careful because it looks like it's a game of words. So we have to be careful with that, right? RMS, this is a very useful parameter, especially when we obtain the response of the shaping waves. Okay, for example, let's suppose that you calculate the roll in irregular waves, right? You can calculate the RMS, right? So it's response in irregular waves. And what we do with this value? Well, what we can do is we can see what other researchers have done. And basically what they do is they eventually recommend a maximum value for this parameter. Okay, so we can use the RMS of a certain motion of the ship in order to evaluate the response, right? So if there is this value goes beyond a certain limit value, that means that probably you need to do something because the ship is moving too much. And probably it's going to affect either the passengers or it can prevent from completing its assignment. So the RMS of a certain parameter, it's a good parameter itself to judge the response of the shaping waves. Okay. So if we go on and see this expression, if this value here, that's the mean of the variable is 0, that means that the variance sigma squared is equal to the mean square. And this is equal to the RMS squared, which is equal to the autocorrelation at tau equal to 0. So this is what we're saying. Okay, if the mean value is equal to 0, then the variance is equal to the mean squared, and that's equal to the autocorrelation at tau equal to 0. So that's what we're saying here. Okay, let's move on. And again, this is something that we are just recalling from your statistics class. Okay. Now, so I would like you to review it again, so you can recall what you learned in your statistics class. Now, let's move on. When we design a ship, for example, or any system that is supporting a random excitation, for example, the waves, of course, we need to determine the largest values. For example, if you want to design a chair, you need to know the largest weight, okay? So that is this chair is going to support, okay? So let's suppose that we are in this class, we are 20 people, well, 22 with Giovanna and myself, okay? So who has the largest weight? But the problem is that next semester or next year, we're going to have a different group of people. So probably the largest weight that this chair is going to support is going to change, okay? Of course, we need to determine this largest value in order to make it support the largest weight, right? So this is very important for us. So in this case, we are showing a time register, and here I am identifying the largest or the local maxima that we can observe. Okay, this is this red dots that you see here, right? So this is the one local maxima, etc. So what we can do is we can take a quick look at this local maxima, okay? And what we can do is we can try to define a new variable, a random variable, and this is only considering the local maxima that the original variable, random variable had, okay? Now, before we go on and proceed in a similar way as we did before, we can see that this value here is very interesting, right? Because this is a maxima, but it's negative, same as this, and that. So in this case, we have 4 maxima which are negative. So it's like an odd parameter, right? So we're going to assume that this occurs, but not very often, okay? If this is the case, we have many of these local maxima which are negative. In this case, what we're going to say is not valid. So in our calculations, we're going to assume that, yeah, we can accept that we have this maxima negative, but its number is very small in general, okay? So let's assume that. So let's take only the positive local maxima. So this is our new variable, right? And we can proceed again and prepare a histogram, right? So this table here, again, we are considering a group of intervals, but you can see immediately that each one of these classes is only positive. Why? Because we are considering only local maxima. So this variable is only positive. Again, we take each one of these and try to determine in which of these intervals is located. Okay, so we have that in the interval of 0.95 as the class, we have the largest number of iterations, of probabilities, right? So we can proceed and again calculate the probability density function. We divide this by the total number, divide the size, and that will give us the probability. But remember, this is a different variable. This is just the variable that considers the local positive maxima of the original phenomena. So it's close, but it's not the same. Okay, we can proceed and plot Okay, for the variable, you see that we are considering only positive values. We start at 0 to the right, and here we have these dots corresponding to these values that we see here. For example, for 0.95, we see that we have 16, which is this number here. And you see that we're trying to make a regression with this blue line. And it looks acceptable, right? See, that means that with this curve, we can approximate the distribution of the observations. Okay, and this function that approximates the distribution of the local maxima is what is the probability that we call the Rayleigh probability density function, right? So it's this way. It has this mathematical way, right? So it's z, that's the probability, that's the variable, sigma squared. So we have to calculate that from the original variable, and again you have the z squared over 2 sigma squared in the exponent. This is to emphasize that we take only positive values, But the important thing here is that this probability can help us to design, because this is just for the maxima, the local maxima of this variable, right? One interesting thing about this variable is that you can integrate it. Okay, so in this case, you can do this process, and for example, the expected value is going to be about 125, the standard deviation, right? So this 1.25, the standard deviation, corresponds to the expected value of this local maxima. Okay. In this case, I would like to do right now. I would like to do. If Giovanna, is there any questions up to here, Giovanna? Giovanna, is there any question up to here, up to this point?
No.
Okay, so in that case, let's do a break here. Let's take a break here, 5-minute break, because my throat needs a rest. Okay, so let's take a 5-minute break.